All right. Good morning, everybody.
Good morning.
How are you doing? Couple of announcements. Yesterday, I posted a new syllabus. I sent you guys an email. Actually, I posted it without the homework, the suggested homeworks, and the sections. So I just uploaded it again in case you printed it out last night. Make sure that you have the suggested homework problems and the sections for each day. Those didn't change, by the way. So if you had them from a previous upload, then you got them. We're going to continue to talk about creating new functions and slope, and we're going to move on to the next section. Okay, so last time we talked about slope, and I think I said it a little too fast. So I'm going to go back to slope and tell you once again, although I imagine pretty much every one of you knows it, but that's okay. Suppose that you have a line, right? And you want to measure the slope. So what do? Well, you draw this triangle. In other words, you draw a right triangle that has hypotenuse being the line. You measure this line. We're going to call this line A, and we're going to call this line B. And the slope is equal to what?
A over B.
That's right, A over B. You can also call this, sometimes you call this the rise over run, right? Is that how you write it? Rise over the run. So how much did you raise? How much did the function go up? And how much to the right did you have to move to go up by that amount? Does it matter exactly where I put the triangle? Could I translate this triangle somewhere different? Yes, because the A and the B are going to be the same. What if I scale the triangle? If I make it smaller, then both A and B get smaller, so the ratio does not change. Okay? Awesome. So you guys have already seen many functions and many slopes. So we're not going to dwell too much on it, but I want to make sure that everybody understands the definition of the slope. Slopes can be big when what happens? How would the function look like that has a large slope? Very steep, right? What does a function look like that has slope 0? Horizontal, right? They're all straight, but this one's horizontal. What about negative slope? How does a function look like that has a negative slope?
Going down.
Going down instead of up, that's right. Okay? And if a function has a very large negative slope, then what does it look like? Steep, but in the opposite direction. Steep going down. That's right. Okay, good. So now let's go back to transforming functions. And let's talk about vertical. Horizontal. Yeah, you're right. Actually, and vertical stretching. Okay, so you got a function. Let's say this is f. And suppose that I multiply the function f by 2. So now I have the function 2f of x. Okay? What that means is that I take the machine, right? In comes x, out comes f of x, and in the end I multiply by 2. How does it transform the function?
Stretch double vertically.
Exactly. It stretches it vertically by 2. So 2 f of x would look like this. All right. What if I wanted to stretch it, so to squeeze it by 2? What would I do? You would... Yes? Multiply by 1/2, that's right. Or you can also divide it by 2, it's the same thing, right? Now, and this again is the trickier one of the two. Just like before, you have the original function f. And suppose that I multiplied inside. So f of 2x, not 2 times f of x, but f of 2x. What happens then? You're stretching it horizontally, but does it get stretched or compressed? Compressed. Once again, if you just saw the first one, you would think, well, it gets stretched by 2. But it's actually the opposite. And this is very similar to what we had before. This is f of 2x. Okay, let's say once more, why would it get squeezed by 2 instead of stretched by 2? Well, let's say that I have a point here. Let's take the point, I don't know, let's say this point is 5, okay? And this point, therefore, is 10, right? So if I evaluate the red function, or the function, this function right here on the left, if I evaluate that function at 5, what I do is I take x equals 5. I have to multiply by 2 because it says f of 2x. So I multiply 5 by 2, I get 10. And then I evaluate f. So the value of this function at 5 is equal to the value of this function at 10. Whatever value it is, I copy it here. Same thing, the value of this function, the red function, at, I don't know, 3 is equal to the value of this other function, the original function, at 6. And if I do this with every point, you see how it gets squeezed by 2. Make sense? Awesome. Okay, now let's talk about mirror image. So it's going to be a very similar story. Suppose I have an original function f of x okay. If I multiply that function but by minus 1, the whole thing, minus 1 times f of x, what happens? Well, all the values of the function get multiplied by minus 1. So if the f of some point is 4, it now becomes minus 4. So the function gets flipped. Yes?
And it gets reflected over the x-axis?
That's right. It gets reflected over the x-axis. And you get something that looks like this. Minus f of x. Once again, that's the easy one. And what if I did not minus f of x, but f of minus x? Sorry? Over the y-axis. Okay. Once again, this is, you see the common theme here. If you do it to x, something happens horizontally. If you do it to the whole thing, something happens vertically. Once again, you should convince yourself why this is the case. Not just learning by heart, but it looks like this. This would be f of minus x. Why is that the case? Well, once again, let's take a number. Let's say this number is minus 2. Here's 2. Suppose I want to evaluate this function at minus 2, right? So x is minus 2. And to evaluate it, I say f of minus x minus minus 2 is 2, right? So I go to the original function and evaluate it at 2. So whatever value the original function has at 2 is the same value of this function at minus 2. And the same thing with 1, minus 1, minus 2, minus 3, minus 4. In other words, this function copies f and puts it all over here. That's why it gets flipped around the y-axis. Okay? Great. Let's do one example of this operation. So, example, draw the function y equals, let's see, 2 minus 2 square root of x plus 1. And find its domain. Okay, so we're going to do this by using what we learned about translations and and stretching. So I'm going to start with the original function. the original function square root of x. This is 1, just to have a scale. Okay? You can also draw x and y if you want. Okay, so what about, let's start with this function. Let's make it closer and closer to this function we have here. Okay, so let's first take this 1 here, and let's calculate this function square root of x plus 1. How does that function look like? It gets shifted by 1 to the left, not up, because if it was up, it would be square root of x plus 1, the whole thing. Right? So if I drew square root of x, the whole thing plus 1, it would get shifted up. But because I'm drawing square root of x plus 1, it gets shifted to the left. Okay. So this is not yet what we're looking for, so we're going to change it a little bit more. Now we're going to multiply it by 2. And what do I get when I multiply by 2? Just multiply by 2. So 2 times square root of x plus 1. Well, it's the same thing, it got stretched vertically, right? So now it goes through this point. Okay. Now let's multiply the whole thing by minus 1. What happens? It gets reflected around the x-axis. Minus 2 square root of x plus 1. Okay, and now finally let's add 2. That 2 in the end will make the function do what? It shifts it up by 2. Okay, so notice that this function went through this point, which is 2. So this function here goes by the point minus 2. So when I shift it up by 2, it actually goes through 0. This is the function 2 minus 2 square root of x plus 1. There you go. So you can do this systematically. It can be a little bit tricky sometimes. I think some ways of doing it are easier than others. It's best, for example, in this case, it seems best to add 2 in the end. Why did it add 2 in the end and not before? Well, you can try adding it earlier, but it might get a little bit more complicated. So it is not an obvious problem. You have to think about it a little bit. Questions? No questions? Okay. So, in that case, let's move over to the next section, which is section 1.5 on exponential functions. All right. So we already talked about exponential functions a little bit, right? Exponential functions. We already talked about the example y equals 2 to the x. And we showed how that function is very strongly growing. Say if this is 1, this is 2, and this is 3, this function goes by, well, let's put this 1, 2, and 3. The function goes by this point right here, the point 0, 1. Why is that? Because 2 to the 0 is 1. Okay? So x, 2 to the x. If x is 0, 2 to the x is 1. If x is 1, 2 to the x is 2. If x is 2, 2 to the x is 4. So you have this increasing function. Like this. What about y equals minus, 1/2 to the x? What happens then? So x 1/2 to the x. So 0 goes to 1, 1 goes to 1/2, 2 goes to 1/2, squared is 1/4, and minus 1 goes to 1/2 to the minus 1, which is 2. So it looks like this. Okay. Do you see some kind of similarity between the two functions? There's some kind of symmetry, right? One seems to be a mirror image of the other. Around the x-axis or the y-axis? Y-axis. But we already figured out how to calculate the mirror image around the y-axis. So how is that possible? This doesn't look anything like what we were writing before. Well, look at this. Y is equal to 1/2 to the x is equal to 1/2 to the x is equal to 2 to the minus x. Right? Okay, so it's the same thing as replacing x by minus x, which flips it around the y-axis. Nice, no? Okay, so bottom line is when the base, we call this the base, when the base in here is bigger than 1, the function is increasing. When the base is less than 1, the function is decreasing. But it looks more or less the same. Let me tell you some algebraic properties of exponential functions. Okay, if you have a number a and you want to calculate a to the x plus y, what is that equal to? It's the same thing as a to the x times a to the y. Okay, so what I would like to suggest to you is to think a special example. For example, x equals 2 and y equals 3. So a to the 2 is a times a, right? A multiplied by a 2 times. A to the 3 is a times a times a. So a to the 5, which is a times a times a 5 times, is the same thing as a times a 2 times and then multiplied by a times a and times a 3 times. So you can think about this formula, if you ever forget, by just setting one special case of the variables x and y. Similarly, a to the x minus y is equal to a to the x divided by a to the y. And a to the x to the y is equal to what? A to the x times y. Okay. So think about it once more in the case of x equals 2 and y equals 3. A to the x is a times a. It's a times a, a multiplied with a twice. And you do that whole thing to the 3. That means you multiply a times a, a times a, a times a 3 times. In the end, you end up a times a 6 times. Okay, it's the same story. And finally, in general, as I just used over there, a to the minus x is equal to 1 over a to the x. Okay, these are all formulas you already probably know. Let me do an example of this. So, example. Let's say b times ab squared divided by 2a squared and the whole thing to the 3. Okay, what is that equal to? Well, that would be b times, and then ab squared is the same thing as a squared times b squared divided by 2 to the 3 times a squared to the 3. 2 to the 3 is 8. A squared to the 3 is a to the 6, but let me just write it like that for now. And so this is equal to b to the 3 times, and now this is a to the 2 divided by a to the 6. I can write as 1 over a to the 4. All right. Just making sure we're all on the same page. So, do you have any questions about how to calculate exponents? Okay, let me ask you a question. Yes. Oh, we do have questions. Yes.
I'm not so sure about how you got the 1.
Okay. So this is b to the 3 times a to the 2 divided by 8a to the 6. Okay? And this a to the 6 can be written as a to the 4 times a to the 2. And then you cancel up and down, right? And you get 1 here and a to the 4 here. In fact, you don't even need to write the 1. You can just leave it like that. That's good. Any other questions? Yes. Here? No? Okay. All right. So if we defined 2 to the x as 2 times 2 times 2 x times, then what do I mean by 2 to the square root of 3? How do you calculate 2 times 2 times 2 square root of 3 times? Sorry?
The cube root of 2?
No. That will be 2 to the 1/3. Right? Yes.
3 to 1 half power.
Sorry?
3 to 1 over 2.
3 to the 1 over 2. Right, so that would be 2 to the 3 to the 1 over, yeah, but how do you compute that, right? Okay, so magic, that's right. So question. How do you compute, let's say, 2 to the square root of 3? How do you do that?
First, you can calculate the square root 3.
Uh-huh.
And what is the range of square root 3? Like square root 3 bigger than and smaller than that.
Okay. So you construct a range for square root of 3. I think that's the right direction. Yes.
Yeah, that's the right direction. I was considering like approaching method.
Approaching method.
Between 1 and 2
Uh-huh.
And then we can approach that like how?
A to the square root of 3 is between, yeah, that's right. Okay, that's exactly what we do. So notice 2 to the p divided by q is equal to qth root of 2 to the p for any p q natural numbers. Do you guys are you guys familiar with this sign, natural numbers? Okay, natural numbers. Okay, so this is just a fancy way of saying if p and q are numbers like 1, 2, 3, 4, and so on and so forth, we can define the value of 2 to the p over q. How? Well, 2 to the p, no problem, and then that to the q to the 1 to the cubic root of q. Qth root of that is also well defined. It's a number whose qth power is 2 to the p. Okay, so that is a well-defined number. So we have that 2 to the any rational number is well-defined. In other words, we can construct it mathematically. So square root of 3 is not a rational number. You know that, right? So how do you define 2 to the square root of 3? Well, what's your name again? Steven? Steven? Can I try your Chinese name?
Yes, sir.
Sorry?
Yeah, sir.
Yufeng? Okay. Yufeng, or Steven, he has suggested to approximate square root of 3 by using rational numbers. I think that's a great idea. Okay? Notice that square root of 3 can be approximated by rational numbers. For example, square root of 3 is similar to 1.7. If anybody has a calculator, you can tell me more precisely what square root of 3 is. I think it's 1.71 and so on and so forth. So you can be more precise and say square root of 3 is roughly equal to 1.71 and so on and so forth. Right? So as you become more and more and more precise with an approximation of square root of 3 using rational numbers, you can get more and more precise about an approximation of 2 to the square root of 3 using rational numbers. So 2 to the square root of 3 is similar to 2 to the 1.7. 2 to the square root of 3 is similar to the 2 to 1.71. And so on and so forth. As it turns out, in the limit, as you make square root of 3 more and more precisely approximated by a rational number, you get a more and more precise value of 2 to the square root of 3. And this has to do with the concept of limits that we will talk about more in detail in a few lectures. Okay? But the point is you can do this closer and closer approximation to get a closer and closer value for 2 to the square root of 3. There you go. So, great. This is how This is how 2 to the square root of 3 is defined as the limit of these approximations. Okay, now let's talk about e. Do you guys remember the number e? Somebody was mentioning it, I think last time. What is e? It's a number like pi, that's right. Do you know more or less the value of e? Okay, it's about 2.71. So the number E okay. I'm going to draw two more exponential functions. I'm going to blow it up quite a bit. This is going to be 1, 1, 2, and minus 1. So, first I'm going to draw um, 2 to the x. Okay, and now I'm going to draw 3 to the x. Three to the x looks more or less like this. This is 3 to the x. And this is 2 to the x. Okay, so okay, so let's suppose that we focus on the slope of these functions at 0. Okay, what is the slope of this function, the function 2 to the x at 0? Well, for slope of the functions at x equals 0, for 2 to the x, the slope is, roughly speaking, 0.7. You can see that it's a little bit less than 1. And for 3 to the x, the slope is roughly 1.1. Okay, so you would think that if you change the base anywhere between 0 and between 2 and 3, that you can get the slope to be equal to 1. Why do we want the slope to be equal to 1? Well, yeah.
For calculus.
Huh?
For calculus.
For calculus, that's right. We're going to see shortly why it is important to have the slope equal to 1. As it turns out, it simplifies calculations a lot. We're going to talk about it more when we talk about actual derivatives. But as it turns out, it's important to have a base such that the slope at 0 is equal to 1. So finding a base such that m is equal to 1 yields the number E, which is approximately equal to 2.71828. Of course it keeps going, right? It doesn't actually end. So that's it. So E is the number such that the function e to the x has slope 1 at 0. Questions? What's that? Steve?
How was it proved?
How is it proved? Well, this particular thing doesn't actually require a proof because it's a numerical situation. You have, you're fine-tuning the number until it gets to that point. So at this point there's really nothing to prove because the number E is defined as the numbers having that property, right?
It's an irrational number.
It's an irrational number, yes.
So how do you prove that? Because you can only approximate, but because it's an irrational number, it keeps on and on.
Yes.
And on, but
Yes.
how do you prove that?
Yeah, so
You have to use calculus.
Don't you use limits for that?
yes, if you want you can use limits, Basically, it's a numerical approximation, right? Again, because we're defining E to be the number that has this property, there's really nothing to prove.
So it's like dividing 3 by 2, where you know you get 0.66666.
You mean 2 by 3?
Or yeah.
It's like dividing 2 by 3?
Eventually,
Yes.
with E, you just solve it and you get that number, but it continues on indefinitely.
Right. You keep you take a powerful computer, let's say, and you start approximating the slope more and more closely, and you get more and more approximations for E.
Yes.
Okay? All right. All right. We still have some time. Actually, we have plenty of time. Maybe we can do some problems from this section. Let's see. Do you have a particular problem that you might be interested in? Yes. Sorry? Okay, this is also done with a calculator, basically. You take a powerful computer and you estimate the slope by looking at the triangles, right? And then you calculate it's roughly equal to 0.7. It's not exactly 0.7. Okay? Actually, it's logarithm of 2. Yes?
Can you explain the last part?
The last part again? You mean this? Okay. So if you look at the slope of the function 2 to the x at 0, okay, that slope is roughly equal to 0.7. If you look at the slope of 3 to the x at 0, that slope is roughly equal to 1.1. So by changing the base, okay, between 2 and 3, we can fine-tune that curve so that the slope is equal to 1. And when you get to a base where the slope is equal to 1, that base is E. All right? Yes, questions from the book? Yes?
Can you do 15?
Okay, number 15. Let's see. Okay, I like it. So, example, y is equal to 1 minus 1/2 e to the minus x. Okay? The idea is to sketch this function. Okay, let's do it. Sketch the function. Okay, so I would start with the function e to the x. Okay, the next thing I would do is I would consider the function e to the minus x instead of the function e to the x. What happens when I replace x with minus x?
It stays the same.
No. It gets reflected on the y-axis, that's right. So e to the minus x looks the same, but reflected on the y-axis. Now we're getting closer to this one. What about, let's multiply it by a constant. Let's multiply it by minus 1/2. What happens if we multiply by minus 1/2? Well, let's multiply by 1/2 first. How's that? When we multiply by 1/2, what happens? It gets squeezed vertically by 2, in a sense, right? It gets stretched by 1/2, which is the same thing as squeezed by 2. Let me do it like this. This is now 1/2 e to the minus x. And now let me do another graph. This is 1 again. When I multiply by 1/2, the function goes by what point? Here, by 1/2, right? This is the function 1/2 e to the minus x. It's good to keep track of some quantitative information about where the function goes through. Now we multiply by by minus 1 on the outside. So minus 1/2 e to the minus x. And we get what? It gets reflected around the x-axis, so we now get it horizontal, like this. And the intersection is at minus 1/2. And finally, we're going to add 1, right? And where does it go through? Where does it intersect the y-axis? 1/2. At 1/2, that's right. So this is 1 minus 1/2 e to the minus x. Okay, notice that it becomes, if you draw this a little bit more carefully, you'll see that the functions have what we call an asymptote. They become closer and closer and closer to 0. If I extended this function like this, it becomes closer and closer to 0. So this function becomes closer and closer to 0 too. And this function becomes closer and closer to 1. That's right. We're going to talk more about asymptotes when we talk about drawing functions. But this is the idea. There you go. What's the domain of this function? The domain of this function is all the real numbers. That's right. By the way, I think I forgot to talk about the domain in the last example. Here, let me go back to this. Remember, I asked you guys to, or we talked about drawing this function, and we wanted to find the domain of this function, the function 2 minus 2 squared of x plus 1. So now that you can see the function, you can see the graph of the function, it's this one right here. This graph. What do you think is the domain of this function?
X bigger or equal negative.
Okay, now these functions look actually quite similar to the exponential function we were talking about before. But there's a big difference. This function actually stops there. This function does not keep going. For example, the square root of x does not keep going. It's only defined up to here. It does keep going that way, but it doesn't keep going this way. So this function stops at this point, and it's only defined from this point on. That means that the domain is made up of the points that are bigger or equal than minus 1. You can write it like that if you want. Or we can use interval notation. Anybody knows this interval notation? The set of all points minus 1 to infinity, that's right. Okay, this is interval notation. We're going to be using it. The square bracket means that it includes the number minus 1. Including minus 1. What about the round bracket in here? It means that it does not include the number infinity. What that means is that it's all the numbers that are bigger than minus 1. Absolutely any real number bigger than minus 1. And the fact that it does not include infinity, it's fine because infinity is not really a number. All right. So, yeah, sorry, I missed that. Okay, so do you have any more questions about the section? We still have about 5 minutes to go. Questions? Okay. Yes? Sorry? Okay. Okay, before I resolve some homework question, I want to make sure, do you guys feel there's some topic that I have not covered that is in the homeworks? Because I was looking at the homeworks and maybe That's why I talked a little bit more about slopes. Yes?
Did you give a 20? Look over 20.
Of what section?
This one.
Okay, you were asking me about 1.2, right? Okay, let's actually do this one, which is this same section. I think that would be better. Okay. G of t is equal to sine of e to the minus t. Okay, what is the domain of this function? That is the question. All right? So, to find the domain of a function, you try to find all the numbers that you can plug in into the argument t. So think about it. If you plug in any number for t, any real number whatsoever, is e to the t, or is it e to the minus t? Is e to the minus t a well-defined real number? Well, why not? Actually it is, yes. The domain of the exponential function e to the x is actually all real numbers. You can take any real number x and plug it into e to the x and you get a real number. Okay? So in fact, you can take any real number t and plug it into e to the minus t and have a well-defined real number. And once you have a number, e to the minus t, can you plug it into the function sine of x to get a number?
Yes.
Are there any restrictions on the argument, on the input of the function sine of x? No. Okay? So because there are no restrictions either on the function e to the minus t or on the sine function, we can say that the domain is all the real numbers. Okay? All right, let me just, before we finish, let me go over again of the syllabus. Is it clear what the different assignments for this course are? Is it clear what the midterms are? Do you guys know about web work? Do you guys know what it is? Yes?
So the homework is updated on the syllabus, or not? Homework didn't change.
The homework didn't change.
So it is on the syllabus.
Now it is on the syllabus. Yes. Yes.
So those are suggested homework problems? Are those the only ones that will come up on the final, or?
No. The homework problems are for your own practice. The motivation that we give you in the class to do them, apart from that, is that the quizzes are going to be partly coming from those problems. In other words, each quiz has about 2 questions, and one of those 2 questions is going to be coming from the homework problems, except that we might change the numbers a little bit.